Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about the kinetic molecular theory. Okay, and the kinetic molecular theory has 5 tenets. Okay, the first one is that gas molecules will travel in continuous random motion. So if we had kind of like a cross section of gas molecules, okay, these gas molecules would just constantly collide with each other. They wouldn't all go into the upper right-hand corner or the bottom left-hand corner. The motion would be completely random, and they'd just be bouncing off of each other. Another thing that we can talk about is that most of the gas is going to be empty space. Like if we took all these molecules, even if there was a lot of them, and put them in the corner, that 99.9% of this container is going to be empty space. And the volume of the molecules is only going to be like 1.1% of the total space. Okay, that's what tenet 2 says. Number 3 says that there's no attractive or repulsive forces, meaning that if they were attracted to each other, as the gas molecules would come together, they would just stick together if there was attractive features. Or if there were repulsive features, as they get close to each other, they would just kind of like not touch. But we don't have that happening with gas molecules. They're just banging off of each other as they collide, and they're just bouncing around, super chaotic type of feature. So there are no attractive or repulsive features with the kinetic molecular theory. The collisions are perfectly elastic, which means that when one molecule collides into the other, okay, energy is transferred perfectly. So if one is going at 0 miles per hour and another one comes in at 5, okay, and this one takes off at 5, that means this one's going to stay still, okay. Another thing is if this one comes in at 5, okay, collides, and this one takes off at 4 miles an hour, that means that this one's still moving at 1. So there's no energy that's lost during these collisions. The collisions are perfectly elastic, and they transfer energy perfectly. Finally, that the average kinetic energy is proportional to the temperature. And I think most people already know this. I think you know that if you heat up a gas, okay, that those molecules will start moving faster, okay? And if they're moving faster, the kinetic energy is going to increase, because what kinetic energy is the energy of motion, okay? Now, if all these things are perfectly true, then the ideal gas law is super accurate. Now, we have this idea of what an ideal gas is versus a real gas. And all gases are real, okay? And what that means is that sometimes they might deviate from this PV equals nRT equation. The PV equals nRT equation is kind of like an estimate, but it's really, really good under certain circumstances, okay? So when the temperatures are really high, which means really, really away from the boiling point of that particular substance, or the pressure is really low, or a combination of both of those things, okay, then the gas is going to really behave according to PV equals nRT, okay? Now, like oxygen gas and nitrogen gas, their boiling point's like really, really low. So even at room temperature, their temperature is really, really far away from the boiling point, and they act like PV equals nRT, okay? As long as we keep that pressure low enough, okay? Now, if we increase the pressure high enough, we start to make kind of like the gas start to look like a liquid, because all of those gas molecules are close to each other. For example, in my drawing here, if I keep on adding molecules in here, then they're getting closer and closer to each other, and they're not really able to bounce off and create all this empty space, okay? Well, if you can't create that empty space, then tenet number 2 is being violated. No longer is 99.9% of this empty space, and if they're not able to get away from each other, they might start being attracted to each other depending on the molecule, okay? So once again, all gases are real, okay? However, most of those gases are going to behave in an ideal fashion where PV equals nRT is going to be a great estimation. It's going to work really, really well as long as the temperatures are high enough, okay, which means away from the boiling point, and the pressures are low enough, okay? However, if one of those things is violated, then the gases are not going to behave in an ideal manner, and we're going to have to use this other, more complicated equation called the van der Waals equation in order to calculate either pressure, volume, moles, or temperature. If you look at the equation, it looks really close to PV equals nRT. Like here's the P, here's the V, and here's the nRT. However, there are adjustments. This piece right here is the adjustment when tenet number 3 is broken, okay? So if the molecules are starting to be attracted to each other, you're going to have an adjustment on the pressure, okay? Likewise, if we keep pressurizing everything and all of a sudden all this space is taken up by more of the molecules than the empty space that I had before, like if I had the before, most of that's empty space. But now when I fill this up, a lot of it's not empty space and the volume of the molecule starts to become significant. So this minus NB is kind of talking about the volume adjustment that we need to make, because no longer is it really looking like an ideal gas where 99.9% of its empty space, okay? Now, when are these things violated? When your temperature gets near the boiling point. So if you cool a gas down enough to where it starts to look like a liquid, you're going to have to use the van der Waals equation. Or when you jack up the pressure, okay? And according to our textbook, it tells us when it's above 10 ATMs, you need to start to consider not using the estimate anymore, and you're going to have to use the van der Waals equation. So ideal gas law, it's perfect. It's a great estimate, and the equation's really easy to use, and it's super effective most of the time. Like 95% of the time, nothing wrong. Maybe 99% of the time. However, we do have some situations when the molecules are starting to be attracted to each other, we need to make an adjustment for it. Or if the volume of the molecule starts to become significant, okay, no longer insignificant, we got to account for that as well. And that's why we have the van der Waals equation. Okay, so use the ideal gas law all the time unless your temperature is near the boiling point or your pressure is above 10 ATM.